Welcome to our demo. My name is Robert Morrow, and I'm the founder and CEO of SigmaX. Today, we'll walk through a demo that will demonstrate the SigmaX end-to-end data flow from data ingest to consumer using Apache open source software and the Open FPGA stack, an open source FPGA software and hardware infrastructure offered by Intel. We'll achieve 100x lower latency and a 20x increase in data ingest using Intel Xeon processors, Intel FPGAs, Open FPGA stack, and our JSON to Arrow parser. First, let me give you some background on our products and our mission here at SigmaX. I'll also talk about one of the key technologies we're using, particularly Open FPGA stack, before we go through the demo. Using Apache Pulsar software alone, we benchmark at an immediate 250% speed increase for streaming versus the competition that utilize things like Kafka, with only a change in the pointer by the customer. Additionally, Pulsar has end-to-end data security versus Kafka and enables data to offload to your cloud of choice. As we have integrated Apache Pulsar with Apache Arrow, the customer gains the added benefit of 20x increased throughput. Our product is highly scalable, up to thousands of compute nodes. As an open source enterprise software company, we have been profitable since inception. We're working closely with our partner Intel to enhance our products while continuing to offer the customer an open source solution to real-time data and AI/ML models. Now I want to talk about Open FPGA Stack, which is one of the key foundational tools that allowed us to take advantage of an FPGA acceleration board and reach those huge time-saving improvements without having to worry about any of the intricacies of the actual FPGA. Open FPGA Stack is a software and hardware infrastructure that Intel provides to FPGA developers through GitHub. Open FPGA Stack, or OFS, enabled us to create our FPGA accelerated workload by providing all the hardware and software source code, documentation, reference examples, and tools we needed to get started. No in-depth FPGA tinkering required. OFS provided the framework and features so we could concentrate on developing our data flow algorithm without worrying about how to change FPGA interfaces or close timing on an FPGA. OFS also enables us to compile and run WinAPI kernels on FPGA platforms, so we have the option to design our custom application in RTL or C++. There's currently 2 code lines for Open FPGA Stack. The code line that enables Intel Stratix 10 FPGA-based development is already open source on github.com/OFS. And the good news is the code line that enables Intel Agilex FPGA-based development is open sourcing later this month in the same GitHub repository, right after the summit. Building a custom FPGA board or workload is easy with OFS. Developers can shop from a range of custom Intel-provided or third-party OFS-enabled boards and use the open source documentation and source code to get started. For our demo today, we'll be using the high-tech, low-profile PCIe card with an Intel Agilex FPGA that supports both Open FPGA Stack and WinAPI. This board is one of many that you can use that are enabled with OFS and WinAPI. Now let's jump into the demo. Like I mentioned, we'll be running our open source SigmaX stack on the high-tech, low-profile PCIe board enabled with Open FPGA Stack and WinAPI. Let's talk about how our SigmaX data management stack, coupled with Intel FPGAs and Open FPGA Stack, improves the efficiency of data being produced to a central broker. Millions of producers can concurrently send information to the broker, millions of consumers retrieve recent data from the broker, and the number of brokers can scale up to thousands. So by first placing the data into Apache Arrow, the brokers can become faster and more responsive by orders of magnitude. We'll be showing the SigmaX accelerated high-use schema pathway for ingesting records into Apache Arrow. This pathway stacks latency and throughput benefits on top of the benefits of an only CPU-based approach by utilizing Intel FPGA acceleration and the Open FPGA stack. Once our data is in Apache Arrow, it is computable as is. No converting from one format to another, no brittle spaghetti connections, reclaimed power, and compute cycles. First, we'll examine the data ingest from ILIX to Bolson. ILIX was developed by SigmaX to generate random JSON sensor data in a predefined schema fast enough to keep up with the hardware accelerator. This is our data source in this example. From ILIX, data will move to Bolson, which runs on top of the Intel FPGA. Bolson conducts the data conversion to Apache Arrow. From Bolson, the Apache Arrow message is received by the broker, Apache Pulsar. From Apache Pulsar, the data is delivered to a client application, which is subscribed to the relevant topic. We first begin by starting up Apache Pulsar Broker, shown on the bottom right. It also spins up a socket for Apache Arrow IPC messages to be produced to. We'll also start up ILLIX here, which we've developed here at SigmaX to generate random JSON sensor data in a predefined schema fast enough to keep up with the hardware accelerator. This is our data source in this example. We'll start the consumer host application, which you'll see connects with Apache Pulsar when we kick off Bolson on the top right, which performs a data conversion to Apache Arrow. What you'll see is 20 JSON records being generated by ILLIX. The FPGA will transform the data into Apache Arrow and produce the data to an Apache Pulsar topic. The host application is subscribed to this topic. Pulsar produces the data to our application. In the upper right, Bolson shows a summary that 20 messages were published. You can see they were received by the consumer application. So we've performed data ingest, accelerated conversion to Apache Arrow using an Intel FPGA and the Open FPGA stack, and transferred data to the consumer application. Using FPGA acceleration and Open FPGA stack, our data conversion workload is 100x faster with 20x more data. This data management workload can be applied to a broad range of applications, including healthcare, insurance, 5G, predictive maintenance, and more. That concludes the demo. Thank you for your time today. To learn more about what was presented today, refer to these links.